Welcome to lecture number 4. Now, this one's not going to be particularly long. You know, I said that I'm going to try to max out at about an hour and 15, hour and 20 minutes in the lectures, but I will try to make them shorter if I can. The idea is that we are also meeting, talking once a week in person, so that counts in your time towards this class. So I'll try not to take up all the time that you think you should be listening to lectures and hearing me talk in the basic 2 lectures in the recorded videos. Try to keep some of that time available for face-to-face talking, but we're going to do whatever we have to do to learn pre-stress concrete. Now, when I took pre-stress concrete at Cal Poly in 1987 or so, I really didn't learn much. We spent 9 of the 10 weeks talking about statically determinate, simply supported beams. At the very end, we kind of talked about indeterminate systems and some of the fun stuff with that. But that was really just, I don't know if you call it anecdotal or what, but we just talked about it. We never did anything. So then I went to Berkeley and had 15 weeks of simply supported, statically determinate beams again, with maybe a week or so of talking about indeterminate systems, but just kind of briefly overviewing those. That's not how my class goes. We are going to get away from statically determinate as fast as we can and get into the fun stuff. Pre-stress concrete really wouldn't make much sense. It never would have been popular had it not been for multi-spans. The ability to fully drape span after span. Continuity is our friend. So we need a method, though, to make sure that you can calculate the moments and shears and all the relevant things about an indeterminate beam or slab, beam in our case. Now in 2011, I just assumed that everybody knew how to use moment distribution to calculate negative moments, and then ultimately positive moments once you pull out the span. Turns out that I assumed that, gave an assignment, and quickly learned that not one UCLA student, undergraduate or graduate, knew how to calculate any moments in an indeterminate system. Could only do simply supported elements. So I mad scrambled and put together a list of, or a set of notes for the next class period, and came in and as quickly as I could taught moment distribution. That's basically where these notes began. Now, I never went to upper management at UCLA and said, hey, it sure is strange at one of the best schools in the country that none of your students can calculate moments in an indeterminate system. But the students did, I think. I don't think they were thrilled that they had not learned that prior to me rapidly teaching it to them. So every year after that, magically, students showed up knowing how to do moment distribution. And that's good. The school listens. I've always said these schools are very good. They listen to the students. You are the paying customer, and they do seem to be responsive to that. That was good and bad, though. It was almost better, I found, when I taught people from scratch how to do it, instead of having them come to me with a variety of different methods of doing moment distribution. Now, nobody had learned it incorrectly. I want to make that clear. But you can learn moment distribution with frames, and then frames have side sway, so you've got frames no side sway, frames with side sway. Moment distribution can get, I don't know if it's complicated, but it can get involved. We are doing the simplest Neanderthal version of moment distribution. We have a flat beam. We do not have frame action. We do not have side sway. So we can eliminate a lot of those things, those complications. And the point is, this is a pre-stress concrete class. It's not an analysis class. So I'm really not here to teach you how to do this. I just need you to have a method so that I can ask you questions and teach you kind of fully the really exciting parts of post-tension concrete. And indeterminacy kind of goes with post-tension concrete. Pre-tension concrete is precast, and they're not going to have any of the fun stuff. Remember pre-Malone and post-Malone. So post-tension concrete relies on cast-in-place concrete, which makes the system indeterminate and fun, and that's where we're going. So even if you know moment distribution, I would like you to listen to how I think you should do it. Now, I will ask you, you will most likely do a moment distribution on both of the exams that I give. You're going to do kind of a complicated moment distribution on the project, and that will be different than what we're going over today, but I will go over it at that time and show you how to do that too. But let's start with the basics of moment distribution. And stick with me, even if you learned a different method. Remember that we have stiffness and carryover factors. So the stiffness factor is when you apply a 1 radian rotation to the end of the beam, there is some moment that it takes to do that, to twist that beam by 1 radian. And the far end, if it is fixed, will also feel an effect. So, this is something you should have learned either in matrix analysis class or mechanics of materials, or somewhere along the line you have learned that moment required for 1 radian is 4 EI over L, as long as EI is constant one end to the other. And for most of our class, that'll be the case. When we get to the project, that won't be the case. We're going to have rigid zones where the beams and the columns intersect, and we're going to add columns. But that comes later. Don't be nervous about that. That's the fun stuff. But right now, if EI is constant, you have no columns, no other member framing in, that moment is 4 EI over L, and the far end will feel a moment of half of that. So your carryover factor is 1/2. So 4 EI over L and 3 EI over L is where we start. For most of what I'm going to give you, we're simplifying things, and we will have the very end of the multi-span beam, if it's a 2-span beam or a 3-span beam, the very end will be a true pin. So the end of the beam will be pinned. So that we can take advantage of that, and that actually just speeds up the moment distribution. So in that case, if in the previous page the far end was fixed, now the far end is a free pin. We know that that moment is going to be 0. That's what we're fundamentally taking advantage of. So to do a 1 radian twist of a beam with constant EI, if the far end is pinned, you should have somewhere along your career learned that that's 3 EI over L. It's not 4 EI over L like it was when this was fixed. With a pin, that is 3 EI over L. So the stiffness, it takes less moment to rotate that 1 radian. That should make sense. And there is no carryover factor because that moment was based on the fact that you knew that the far end was 0. So any moment that we add at this end, none of it will transfer over to the far end. Okay, carryover factor is 0. Stiffness is 3 EI over L. The idea in moment distribution is that we start with all of the joints completely fixed. So they can't move, they can't rotate, we're locked in every one of the spans. For the vast majority, if not 100% of this course, we will be looking at uniform distributed loads. Every once in a while on a test, I will put a point load on, or a point load will be created by the pre-stressing, and we'll have to incorporate that point load into the fixed end moment. I will always give you the fixed end moment in that case, or the equation for it, if that comes up. But for basically all the project and effectively all the homework assignments, you will have a uniform load in this class. So a uniform load on a beam with 2 fixed ends with constant EI, one end to the other, has fixed end moments of WL squared over 12. Again, that should be something that's familiar to you. Either you learned that in your own moment distribution lesson, or matrix analysis brings all this together. Instead of doing a moment distribution, you transpose and invert and do all the fun stuff to matrices and solve them simultaneously in a massive amount of simultaneous equation solving. That's for the mathematicians to do. For me, I'll do the moment distribution. So, fixed end moments, WL squared over 12. Then we have something called distribution factors. Distribution factor is simply a way of stating that if you have an unbalanced moment, some of it's going to go to one side of the beam and some of it's going to go to the other side. And that's going to be based on these stiffness factors that we've already calculated. So let's get right into it. Here's a 3-span beam, 3 kips a foot on the first span, 2 kips a foot on the second, 1 on the third, changing various span dimensions. Start with finding the stiffness factor. Now, stiffness BA means I am standing at B and I am looking toward A. I'm looking at the stiffness of this end of this beam segment. Now, we just discussed if the far end of that is truly pinned. Now, these are all pins, but that doesn't make the end of the beam pinned. The far end being pinned means that when it's all over, we know that that moment's going to be 0. So if at the far end of wherever we are standing and looking, if that far end we know is going to be 0, then we use 3EI over L. It will hasten our moment distribution. So in that case, KAB is 3EI over L. EI is constant, so I'll just leave it in there, but it's going to drop out in the wash pretty soon. L is 28, so we have 3 over 28. That is standing at B, looking at A. Stiffness BC means I am standing at B and looking towards C. Now that far end, while it's sitting on a pinned support, is not a pinned end of a beam. And that moment is not going to be 0 when we're all done with this. So we cannot use the 3EI over L trick or advantage. So that's 4EI over L. If I'm standing here at B looking to C, that's going to be a fixed end. So 4EI over L, L is 32, EI is going to cancel out. Do the same thing C to B. I'm standing at C. I'm looking over at B. That end, while on a pin, is not a pinned end of this beam. This beam continues through that joint. Therefore, I'm using 4EI over L. And the moment at this point will not be 0 when we're all done with this. So that's the dead giveaway. We can't use 3EI over L. So that's got its own 4EI over L. And then we go back to CD. I'm standing at C. I'm looking to D. That will be M equals 0 when we're all done. So we're going to use the 3EI there. So now we're going to look at the distribution factors. Distribution factors, again, are the basic proportion on one side of the beam and the other side of the beam of what unbalanced moment will be distributed to each side. So at A, any unbalanced moment will be 100% distributed back to the beam. Any unbalanced moment at D, 100% will go back here. So the distribution factor at AB and DC is 1. We only have one element framing into that joint, so it's got to be responsible for 100% of any unbalanced moment. In these, in the interiors, we've got 2 beam segments coming into the same joint, so we're trying to figure out what percentage goes here and what percentage goes here. So if I want to know what percentage goes on the B to A side, I look at the stiffness of B to A, divided by the stiffness of B to A plus B to C. So this beam has a stiffness, this beam has a stiffness. If I want to know the proportion that this beam is going to take, I take its stiffness divided by the sum of all the stiffnesses going into that joint. So the stiffness of BA we had established was 3 EI, and the EIs are dropping out now, over that L, divided by the stiffness of both sides. So stiffness of B to A again was that same 3 over 28 plus 4 over 32. So that's the stiffness here. So the proportion of an unbalanced moment going to the B to A side will be 46.15%. Now, since we only have 2 elements framing in to this joint, 2 elements framing into this joint, the other joint has to make up the difference. So we could do the calculation, or we can just say 100% minus 46.15% is 53.85%. We'll go to this side. Distribution factor from C to B follows the same logic. We're looking at the distribution, the stiffness over here divided by the stiffness here plus the stiffness there. Stiffness from C to B was 4 EI over 32. EIs fall out. The sum of both joints is that same C to B plus C to D, and C to D being the 3 EI over L. So 62.5% of any unbalanced moment will go to this side, this beam segment, on the left side of joint C, and the remaining 37.5% will go to this side, this beam segment. So far, so good. Let's calculate the fixed end moments. Fairly straightforward. WL squared over 12 in each span. The first span, W is 3 kips a foot. L is 28. WL squared over 12, 196. WL squared over 12 in span BC, 170.67. WL squared span CD, 133.33. So we've got everything we need to set up the moment distribution now. So remember that the beginning of this process, all of these joints start off as fixed. That's how I want you to think about it. These joints are all, everything's fixed. Everything's locked in place. Every joint is locked, cannot rotate. That's how we start. So we've got our carryover factors here. Remember, any unbalanced moment, half's going to go that way. But any unbalanced moment here, 0 goes that way. So, because we're taking advantage of that 3 EI over L. In this direction, the stiffness was based on 3 EI over L, with the far end having 0 moment. So, and same thing over here. For the middle span, the carryover factor in both directions will be the 0.5. We've established the percentage at each joint that any unbalanced moment will be distributed to each side. And here are our fixed end moments. Our fixed end moments are based on the right hand rule. So for this beam, let's use real drawing. So this is that beam. If you take your right hand, and remember this is trying, oh, that's not pretty. Let's do that better. Not much better, but you get the point. Take your right hand, and we have got to hold this beam from rotating. So your right hand is creating that counterclockwise moment, and your thumb's coming at you. So your thumb is a big part of this. Hopefully you have opposing thumbs like I do. This tells you it's positive. Your thumb is coming up at you. This is numerically going to be a positive number. That's why that is positive. Take that same right hand to hold the other end in place. You've got to point your thumb down into the page and rotate it clockwise. So that's a negative. Your thumb is going into the page. That creates the negative. We need to keep the signs in the moment distribution accounted for so that we're getting equilibrium at the joint and we know it. Okay, so each one of these is set up that way. And by the way, remember, we're going to have a load case where the loads are going up. So that same situation, and you got to be careful. Very shortly, we're going to have loads going up as one of our load cases. So the deflected shape is going like that, and you're actually going to have moments going the other direction. So if this was pre-stressed concrete load case with the loads going up, this would end up getting the negative sign and this would get the positive sign. We're not quite there yet, but we're getting close. Okay, so we're all set up. All the joints are set. The fixed end moments are in place. Right hand rule has been implemented. And this is the moment diagram at this moment in time, before we've done any distributions. So notice that we know that this is going to go to 0, but it's not 0 now. We notice that this is going to go to 0. Well, we know that. It's not 0 now. And when we're all done with this, these two numbers need to be the same as each other, and both of these will need to be the same. They're not right now. There is an unbalanced moment in each one of those joints. We can't have an unbalanced moment, so that's our job, to do a moment distribution to get rid of that. And if you want to look at the deflected shape, this is what the deflected shape looks like. Every joint is completely flat, so it has no rotation at this point. First thing we're going to do is release both this joint and this joint. That's the easy thing to do. We know those are going to 0. If we can just get those out of the way, because we utilize the 3EI over L, once we get rid of those joints or get those in equilibrium, we won't have to worry about those joints anymore. We're not going to distribute back out there. So, to put this joint in equilibrium, it's got 196 foot kips that it doesn't really have, or we know it's not going to have when it's over. So we've got to put a negative 196 there. That carryover factor, remember, half of that will go to this joint. Same thing over here. We're starting off with a joint that has negative 133.33 foot kips. We know we're going to end up at 0, so we must put a positive 133.33. We end up with 0 at both locations. This has got to carry over half of that to the joint over. Okay? So the situation that we're in now, we actually just made this unbalanced moment and this one actually worse than they were before, I believe. So those are way out of balance, out of equilibrium right now. These joints are now in equilibrium and they're done. They're happy. They're just going to stay where they are. The trick for us is to get both of these joints into equilibrium. And we're going to start one at a time. So this is the current deflected shape. We have a rotation at each one of these ends, but we're still locked in the interior joints. So right now we have 294 foot kips trying to bend that way, and 170.67 foot kips trying to bend this way. Doesn't take a rocket scientist to realize that this joint will want to ultimately rotate in that direction. So we're expecting a joint rotation of something like this when we're all said and done. At least when we're done iterating this, putting this first joint in equilibrium. This is going to decrease, this is going to increase. They're going to find some equilibrium. So notice that we're out of balance by 123.33 foot kips. The way to do that, and if you haven't done this or you're refreshing, get your calculators out, add up these numbers. These numbers should equal negative 123.33. You actually don't need that. I'm just adding that up to show you what that number is. So you've added those up. You all agree that added up to negative 123.33. So to put this joint in equilibrium, I need to add positive 123.33 foot kips. Now what does that look like in my moment distribution? Again, you added these up, got negative 123.33. We have to add positive 123.33. And the way we do that is 46.15% will go to this side, and 53.85% will go to this side. So that's the 123.33 positive to get this joint in equilibrium. That's how much goes to this side and how much goes to this side. Now at this point, we add these up, and we add these up. And they should add up to the same number with a different sign. In other words, you add these two together and you get 0. Or you add all of these numbers up and you get 0. That means the joint's in equilibrium. There's no unbalanced moment right now. So that joint, yay, is in equilibrium. This is in equilibrium. This is in equilibrium. We're almost good, except for the fact that by putting this joint in equilibrium, we just affected the far end of this beam. So we have a carryover factor. We have to carry over half of the 66.41 to the joint C. 33.21 comes over here. Okay, so now I've added these up, and I've added these up, and I'm showing you that that's our unbalanced moment condition. We are unbalanced. That joint is unbalanced by 62.54 foot kips. Again, I want you to add up these numbers. Use your calculator. You should be coming up with a positive 62.54 when you add up those numbers. So to put that joint in equilibrium, we have to add negative 62.54 foot kips. And that's what we're doing here. So remember, you added up all of these. You get 62.54. We're now applying a negative 62.54 to the joint to put it in equilibrium. 62.5% of that unbalanced moment will go to this side, and 37.5% of that will go to this side. So since you have your calculator, negative 62.54 times 0.625 should give you that negative 39.09. Same thing on this side. So now we add up all these numbers, and we add up all these numbers, and we get the same number with just a sign difference there. So this joint now is in equilibrium. This one's in equilibrium, this one's in equilibrium, this one was in equilibrium, but it's not anymore. It's not anymore because while we were messing around with this joint, we affected that one. That carryover factor again. So we had to add the 39.09 negative here. That affected and put this joint that we had worked so hard to put in equilibrium out of equilibrium again. Out of equilibrium by 19.55, or 19.6 as I say there. Probably should have put the same number there. There we go. It's fixed. This joint's out of equilibrium. So, what do? We put that joint back in equilibrium. By doing that, we're going to affect that joint. Then we're going to put this one back in equilibrium, and we're going to affect that joint. We're just going to bounce back and forth until the numbers become so small that we don't have to do this anymore. So where were we? Right here, we had negative 19.55. Remember, you can add all these numbers up. These numbers were already added up to 0. We had already put that joint in equilibrium. So while you could now add up all of these numbers if you really felt like it, you have a new calculator and you just love using it, you can do that. Except that you already know that these numbers added up to 0. So not much reason to put those in the mix. This joint is only out of equilibrium by the 19.55 foot kips. I'm expecting Camtasia to crap out. It usually does about this point, so I'm watching it. So instead of adding up all the numbers that you previously had, just recognize that this joint is now only out of equilibrium by what got carried over from here. Therefore, I just changed the sign 19.55. Okay, let's not do that. Needs to go here, and 46.15% of that goes here, and 53.85% of that goes there. I think you're seeing where we're going. By doing that, by adding that 10.53 there, we have to carry this over. Again, all of these numbers added up to 0. And if you don't believe me, add them up. You could, and a lot of students come to me with, thinking that they constantly need to go back and add up all numbers in the joint. That will actually mess you up when we get to the project. So I'd rather you really think about what is happening and understand that you were in equilibrium at this point. So all that added up to 0. I'm going to say something that's going to confuse you now. Even when we get to the project and you have columns introduced, those numbers won't necessarily add up to 0, but the point still will be that your joint was in equilibrium. You set it in equilibrium every time we go through a step. So the only way it's out of equilibrium is by whatever you sent over since it was put in equilibrium. So this 5.27 gets distributed a negative 62.5% here and 37.5% there. We just go back and forth on this until the numbers are really getting so small. In fact, sometimes you'll see that you're just sending the same number back and forth. You'll know you're done. You don't necessarily have to go that far, but I'm a fan of accuracy. And remember, the end game in this course is going to be that you are using our computer program, the one my father wrote, PT Data. You're going to do a project that has columns, it has everything in it. You're going to do it entirely by hand. And you're trying to match the output of a computer program. So accuracy is important. There are times in practice when we, only have to be close enough for government work, as they say. But I used to have a geotechnical professor, for foundations. And he'd always say that. He'd always say it's close enough for government work, particularly in soils engineering. I don't know what that meant. None of us knew what that meant, but boy, I've been saying that the rest of my life. Just something that's close enough is close enough for government work. I assume back then government work didn't have to be all that accurate. Where that came from, I don't know, but I still use those same sayings today. So anyway, we've now completed the moment distribution. So Camtasia loves to just collapse on me right at about 32 minutes. I think it seems to want to limit me to about a 30-minute stretch of video, and then it just falls apart. So if you notice that there's kind of a gap sound, that's because it's not my fault. It's Camtasia's fault. So we're back again. What's so great about moment distribution? You end up with these negative moments. What's great about it is now every part of this beam is statically determinate now. Pretty sure I had one kip a foot on this one. But now that you know what that end moment is, you can now calculate the shear on the left, the shear on the right. You can draw the shear diagram. And from that, you can draw the moment diagram too. So, woo, look at that. So the moment distribution literally makes every span now statically determinate. So I could jump to the third, fourth span. Just look, if I was interested in knowing what the positive moment was there. I think I had 2 kips a foot. I have everything I need now to calculate the shear in the left, the shear on the right, shear diagram, the moment diagram for that span. As long as I know what the negative moments are in any span, that is now a statically determinate span. I can use statics from that point forward to find out everything else. That's the beauty. That's why we love moment distribution. It's just the negative moments that I need. I can do everything else on my own from there. And we will. I have something else in here, and you have it in the notes, and I wrote this because I was trying to help clarify life and reason for living and things like that. This turned out to be more confusing. It's still in the notes, and I leave it there. My thought process was to show you something more similar to what you were going to do when you get to the project. And what I've learned over the years is it's better to just get to the project and show you how to do it then than to try to confuse you at this point. I will walk you through what you're looking at, and you can cover your ears and your eyes right now if you don't want to hear about it. And that may end up being better. It would be less confusing. Everything we just did is the way I want you to approach the homework assignments, the exams. Just use the 3EI over L to the far end pinned. Use the 4EI over L on the internal spans, and you'll be fine. We'll just stick with that. There is another way to do this, and maybe this is the way you learn, so I will present the fact that at least I'm aware that you can do that. We could have said, I don't want to take advantage, or I don't realize, or I don't believe that 3EI over L is the right stiffness factor if the far end is pinned, and the moment will end up being 0 at the 2 far ends of this multi-span beam. So I could just use 4EI over L. I could calculate different distribution factors based on that. So now this distribution factor BA is different All of these are now different. They have changed because I have started with the assumption that everything is fixed. All ends of all members are fixed. That's okay. I can do that. It will come out in the wash, the same exact answer. So distribution factors, AB and DC are still 1. Carryover factor is now 0.5 in both directions because now we're going to fully distribute back out to the end joints, back in, back out, back in. We're going to include them so they don't feel left out. Maybe this is the way you learned it, and I don't. If this is confusing, then just pretend like I never said it. But with these new distribution factors, all based on 4 EI over L, start off with the same fixed end moments, but life is a little bit different now. We're going to add the negative 196 and the positive 133 and still carry over 0.5 in that direction. The distribution percent is different, so the approach was the same. But in this case, because we didn't take advantage of the fact that we just knew that this moment was going to be 0, we have to send half of that back out. Then we put this joint in equilibrium again because it's there's only one beam framing into this joint and the distribution factor is 1. No matter what we send out here, 32.87, we're going to put back negative 32.87. So that will send half of that back over to here. And we'll put that back in equilibrium. That's going to affect this joint. But the process is a little more involved, has more steps to it, and always involves distributing out to the outside. So if you learned putting everything at 4 EI over L, and that's the way you're comfortable with it, and you want to stick with it, this is the moment distribution then that you have to do. You're going to do more steps, you're going to take more time. Unfortunately, you're going to take more valuable test time, but I always get a few students that want to do it this way because they learned it that way. And that's why I said it would almost be better if I was the only one that ever taught you this. I don't recommend doing this. If it's confusing to you, forget I ever said it. You can go through this if you want to get more comfortable with moment distribution. You'll end up with the same exact answers. We didn't have to take advantage of the fact that the ends are pinned. We knew they were going to be 0, therefore we could adjust our stiffness factors to take advantage of that. That's where the 3 EI over L came in. If you don't want to do that, you don't have to do that, but you're in for a little bit longer trek. I put cantilevers on a lot of times. I love cantilevers. The post-tension concrete loves cantilevers. Cast-in-place concrete loves cantilevers. Steel has to weld a lot to create a cantilever. Wood has to basically frame over a post. So at one level you can do a cantilever on wood, but if you're doing 3, 4, 5-story building, you're allowed to get a 5-story building in wood. Cantilevering is not very easy. You really have to jump through some hoops and do some strange framing to building cantilevers into wood. Same into steel. It's just there's a premium and an expense and a complication. There's no premium, expense, or complication in doing it in cast-in-place concrete, really. And in post-tension concrete, there really isn't any at all. We actually prefer it because if you think about how we're going to drape our tendons, we want to drape high over these supports anyway. So having a cantilever actually allows us to increase the drape at that first interior support. So not only do we like the cantilevers, it actually makes part of our lives easier and better. In cast-in-place concrete, at some point the cantilever will get long and it will start drooping. Not drawing particularly well. This will hang down, create some problems, creep over time. Post-tension concrete, we solve that. We actually just use the post-tensioning, pick up the the sag or the deflection, and we can make ours flat. So we're showing off a little bit, it's true. But when you can, you do it. Okay, so analytically, I want you to be able to handle cantilevers because I like to put them on homework assignments. They'll show up on tests. I don't put them in your project, but you will need to understand how to do a moment distribution with a cantilever. Now, with all that said, I'm taking the same example. Oh, I just noticed I didn't have one kip a foot. I had 3 in that bag. You guys will understand that and fix that. My point was still the same. Once you have the negative moments, you can, each span is statically determinate. Okay, all I've done is take that same example and added a cantilever, a 10-foot cantilever. That didn't change anything about the joint stiffnesses, the 3EI over L. I know that's confusing. A lot of people think that as soon as I just stick on a piece hanging out here, that I can't use the fact that that stiffness in that direction was 3EI over L. It still is. Sticking on a statically determinate piece hanging over doesn't change anything about our analysis. It's unfortunate. I put a cantilever on a test, and next thing I know, I'm seeing somebody calculate the stiffness of the cantilever, trying to work it in, trying to figure out what percent goes over here and what percent goes over here. It doesn't change anything about the analysis. There's only one thing you need to do if I give you a cantilever. That cantilever, regardless of if this is 1 span, 2 span, 3 spans, 9 spans, that cantilever is statically determinate. Whatever load is on a 10-foot cantilever, WL squared over 2 is going to be the moment right here. Doesn't matter what that is, what these spans are, anything about that. Can't change statics because it's your best friend. So that just becomes, instead of being 0, instead of knowing that we're going to end at 0 in the moment distribution, we actually know that we're going to end at the statically required cantilever moment. That's the only change. That's the only difference in this. So, please be careful. Those stiffness factors, we're using the 3EI over L. We're using the fact that we know that this is 0. The fact that this was 0 before, now it's just going to be 50, doesn't change anything. That didn't change the stiffness. And this may be hard. Let's use real pen. Remember, we were rotating that joint. Yeah. Don't look at that. Okay. We were rotating that. I didn't even write that correctly. It's more like that. That was going to have no moment. It's still going to have no moment, even if I just stuck a piece on it. It's just hanging out and flapping in the breeze. So that's really the best way to think about it. The fact that I extend an element past that joint doesn't change anything about the fact that to twist that 1 radian with that being a pin didn't change the stiffness of doing that. So that may or may not seem like it makes sense, but it needs to make sense. It does. Spend time thinking about it. So again, the only difference is instead of setting this and knowing that this is 0, we're going to set up the fixed end moments just like we did before. Everything about this is exactly the same as it was before. All of this. In fact, all this starts off the exact same way. The difference is right-hand rule, I added in a positive 50 there. So instead of ending, this is going to have to end at 50. This is going to have to end at negative 50. So I need to add whatever amount of moment is necessary such that that is negative 50. And in this case, instead of adding like I normally would have done to get to 0, I would have added positive 133.33 here. Now I'm adding 83.33. So the end result is negative 50, offset the 50 static moment that I have in the cantilever. And that's the difference. But now, instead of positive 133.33 and carrying that over, I'm carrying over half of 83.33. That's it. Everything then launches off, does the same thing it did before. These numbers, of course, are no longer the same as they were before, but the process is exactly the same. So, that's the magic, nothing up my sleeve, with adding a cantilever. These moments, statically indeterminate moments, depended on the moment distribution. This moment, statically determinate. Didn't depend whatsoever on the fact that it was an indeterminate system inside. Okay, there we go. I told you this wouldn't be a particularly long lecture. For those of you really confident in moment distribution, maybe you stopped watching. But I would strongly suggest doing it this way. Basically, just about every homework assignment you're going to do from just about this point forward, and in the project and on the exams, is going to include moment distribution. So I've never had a student not get this. Some of them struggle a little bit in the beginning. Everybody eventually becomes an expert at moment distribution, even though I wasn't intending to teach that. This is a pre-stressed concrete class, not an analysis class. But so now we're all on the same page, and we can move forward at this point and start really looking at the exciting things about post-tension concrete. So, see you at the next lecture.